Hello! Today it's PLLs. So I'm going to give you an introduction to PLLs, but I don't expect you to actually know everything after this introduction. PLLs are a very complex analog block, and it's again a block that people specialize in and become experts in. But the general principles are possible to get a grasp on, to get started. So first, why do we need phase-locked loops or delay-locked loops or frequency-locked loops? What do we actually use those for? And then I'll give a rough introduction to PLLs. So let's go over to the slides. Yeah, why? So if you take a random dev kit, this is a dev kit from Nordic Semiconductor. It seems to be the 52832. You will notice you have the IC, and then around the IC you will have components. So for example, we have number one here that is a 32 megahertz crystal, and number two here is a 32 kilohertz crystal, or it might actually be 32768 to get a real-time clock. So you can divide by 32768, which should be 2 to the power of 14? No, 15? To get a second. And then there are other passive components like the inductor for the DC-DC that we talked about last time, and you also have an integrated PCB antenna. But today it's about the clocks. So there is a reason why these crystals are there. The 32 megahertz crystal, that is the frequency reference for the radio that sits inside this chip. This is a Bluetooth chip. And to create a really precise frequency, we need a reference, and that reference is this almost, I don't know if it's mechanical, but the crystal itself resonates at a very particular frequency as long as you drive it correctly. And it can be very precise. You can buy crystals that have sort of plus minus 20 ppm. However, on the chip, the CPU might run at 64 megahertz, and the radio, well, when we transmit for Bluetooth signals, well, it's between 2.4 gigahertz and 2.48 gigahertz. But we don't have an external reference for all those different frequencies, which means we need to use our single precise frequency, and we need to multiply it somehow to generate all the different clocks needed for the CPU and needed for the radio and so on. Which means inside the chip there will be a full sort of clocking system. You'll have something called a crystal oscillator, a driver, that actually uses the external crystal to resonate and generate a very precise, low noise, 32 megahertz clock. And then we have what we call phase-locked loops. So they are a type of block which can generate, well, it could generate the same frequency, 32 megahertz, or we can generate any different one. And we'll look more into that later. And there will be PLLs in the system, there'll be probably a PLL in the radio, and that allows us to, for example, run the microcontroller at whatever frequency we choose for that particular chip. Now the low frequency crystal, that's often used for sort of real-time clock. The fact that maybe you want your device to sleep for a second and then wake up precisely at 1 second later. And this is used in Bluetooth communication, where when you're in connection in a Bluetooth system, you actually schedule when in time you're supposed to wake up and listen to the radio or listen for packets and transmit packets. Those are scheduled events, which allows Bluetooth to be low power, because you can turn off the whole chip and just run this real-time clock and then wake up precisely when you need to. Now, some customers don't want to buy the external crystal, so it is also possible to use internal oscillators based on resistors and capacitors to generate this real-time clock, but it will not be as precise because you can easily buy 30 ppm low frequency crystals, while RC oscillators, they're not that easy to get below plus minus 500 ppm, which is needed for Bluetooth. So for all digital, well, not all, but most digital systems, we need a clock, because the fundamental idea behind digital is that we have a set of input registers and a set of output registers. In between those, we have some combinatorial logic. So this is your always comb and your always FF parts in your system Verilog. The whole idea is that the data coming in, so the B in this case, only needs to be correct when the clock strikes. So as long as, well, it can transition, the B can go 0, 1, 0, 0, 0, 1, and so on. As long as it's correct when the clock strikes, then the system will work. And that's where the type of timing analysis that you have to do for every single path in a chip, which might be millions to billions of paths, you have to check every single one of them and make sure that the data that comes out of Y here has enough time to propagate through the logic and arrive at B early enough. So that's called the setup time. And then you also have a concept about hold time, because as soon as, so you can see these two registers for the input and output, they are clocked by the same clock. Actually, I have forgotten to name that one, but the clock is the one going into the triangles. So since the registers are clocked by the same clock, as soon as the clock strikes, the Y output will also start to change. And it's important that the B value is kept stable. So long that the output register is able to capture the data. That is called the hold time. Now, the cadence between each clock cycle, that's our frequency. And that's what we need to generate. And on a digital chip, or in a chip with lots of digital logic, we might be running many, many different clocks. And all of them need some precision, because all these setup and hold times, imagine if they vary all over the place, or if a clock varies all over the place, it becomes hard to analyze. So quite often the clock that digital relies on, it needs to be precise, but nowhere near as precise as the radio needed for the radio. Okay, so PLLs, extremely important block. It's a fundamental system infrastructure type of block. It will be there if you have digital logic. Well, if you have multiple digital logic systems that need to talk to each other at different clock frequencies, then it's definitely there. Because if you have one block, digital block running at 32 megahertz, you have another one running at 64, you better make sure that in the transition between the boundaries between those two clock domains, the clock is phase aligned. You can actually make clock bridges and asynchronous logic, but quite often that's more involved, or it adds complexity. Now, the fundamental concept we've talked about before, and it's the concept of feedback. So it's the idea that given any input, now this doesn't have to be voltage, then I can generate an output, which also doesn't need to be voltage. It can be phase, it can be frequency, it can be whatever. And as long as I feed a model of that output back in the same domain, so if the output here was frequency, and I feed it back, and I am comparing to a low frequency, for example, then I need to compare it to the same frequency. And I add some sort of loop filter, some filter with gain. It's possible to prove that as long as you have enough gain, infinite gain, in this H of S, then you can force the output to be equal to the input. Now this is interesting in the type of phase lock loops, because what we could do is, let's say the output here was a frequency and it was a high frequency, 2400 megahertz. If I put a divider, I can divide that output frequency, the 2400 megahertz, by 75, and that gives me 32 megahertz. Now, if I somehow can compare my down-divided output clock with my extremely precise 32 megahertz crystal oscillator clock, and I could take the error between those two, feed it into a loop filter, and then control an oscillator that changes the frequency of the output, then this becomes a feedback loop. And this is fundamentally a PLL, a phase lock loop, because what will happen, well, actually it doesn't need to be phase, but most accurate is phase, because then we align the phase of the output clock, the FO, with the phase of the input clock. You can actually do this with digital also, or you can actually use a digitally controlled oscillator, and you can feedback, just measure the frequency, and you compare the frequency, and you have some sort of loop filter to reduce the error. And then it becomes a frequency lock loop. You can also do this with delays, and there's a link in the syllabus to a paper on delay lock loops. And they all have different applications, whether you need phase lined or when you need delay, or you just need roughly accurate frequency. And also in a PLL, it is possible to make the oscillator that generates the output frequency. You can actually also make that digitally controlled. And that's quite common today, that you'll find in research papers the HFS and the phase comparison and the dividers, and well, it might look slightly different, but in the end, it's what we call an all-digital PLL, where most of the HFS, or the filter that we put in here, that is in the digital domain, which is nice, because then we can actually change HFS as time moves on, which is much harder in analog. So the way I'm going to structure it today is I'm going to go through each of the blocks in a PLL. So principally, we have an output clock that's called CK. We have a reference, and let me go all the way up. Let's do it like this. Yeah. So the output clock, and we have our reference clock. That is the, for example, 32 megahertz. Then we divide by 32. Sorry, in this case, I probably seems like I've used 16 megahertz as the input. CK ref is 16 megahertz. We divide the output by 32, and we get 16. So we're comparing to the same frequency, but the phase is gonna drift. And then we have a phase detector, something that can compare the reference clock with the down divided clock and give us an error signal. This error signal feeds into what we call a charge bump. So in this case, we can inject some current, or we can take away some, or inject some charge or take away some charge. That feeds into a low pass filter, which is buffered, and then controlling the VDD of a ring oscillator, which is actually our oscillator. So this whole thing becomes a feedback loop, and it can work if you make it right. The other blocks here, bias and the kick, that's just a couple of blocks to make it biased. So we get a 1 microamp bias current coming in, it feeds into a diode connected NMOS, and that generates a voltage for the charge pump, which generates our up and down currents. And then the kick module here, that's just to accelerate startup. That's why there's two inputs to the loop filter, to just set the voltages on the loop filter roughly correct when we power up the module. That's not important now. But a very important point is PLLs absolutely need calculation. There is no way. Well, it's unlikely that if you just sit down and you draw your schematics and you try to simulate, then it's unlikely that it's going to work. Most likely it will not work, and it will be very hard to actually tune in the different components, so the charge pump, the loop filter, the oscillator of the PLL, without sitting down and analyzing the PLL on a piece of paper or in Python or with calculation. So it's one of the few analog designs where you simply cannot do a cowboy design. And what I mean by cowboy design is that you sit down, you throw some transistors together, and you hope for the best, which actually works with a lot of analog design, but for PLLs, forget about it. Will not work. You have to analyze them. Now, one thing to realize is that PLLs are, well, they have clocks, which means they're sort of nonlinear systems. Voltages go up and down, and it's not a linear system in the voltage domain or time domain. However, it is possible to linearize the PLL in the phase domain. So phase is just the integral of frequency, and it turns out, well, I guess this was back in the day of hand calculation with piece of paper. They discovered that, well, in phase, you can actually analyze PLLs with a linear model. And this is quite common with discrete time systems, as long as your frequency, or as long as the discrete time components are high frequency and your bandwidth is quite low, then it's possible to assume that you have a linear system, in this case, but only in the phase domain. This is similar to what we looked into with the bilinear transform, that the bilinear transform that works well between the Z domain and the S domain, as long as you have, well, maybe 10 times the sampling frequency compared to your bandwidth. And it's a similar thing in PLLs. There's a rule of thumb that says that your reference frequency coming in here, let's assume 16 megahertz, that needs to be maybe 10 times higher than the pole or the bandwidth of the loop filter. I think that's roughly the approximation. But if we do that, if we assume that those things apply, then we can create a linear model. What you're seeing in the picture now is the S domain description of the different blocks. So we have the oscillator, which has a gain divided by S. We have a 1 over N, so that's just our divider. It has a gain of 1 over N. There is a gain for the phase detector, and then there's a gain and a transfer function for the loop filter. And if you put them all together, it's possible to show that the loop transfer function is given by the oscillator times the phase detector times the gain of the loop filter times the transfer function of the loop filter, and divide by n times s. Now, an interesting thing happens in PLLs. So let's look at the DC gain. So let's, for example, assume that our loop filter here, that has a low pass response, which means that low frequency, it's basically a constant. It doesn't change much with frequency. It's only at high frequency that it actually rolls off and becomes less. So let's assume that's a constant. And then we insert 0 into this loop filter equation. Well, if we insert 0 frequency, so we take the S, we replace it by j omega, we insert 0, then we get an infinite gain here. So PLLs with a VCO like this is one of the few cases where you actually can have infinite gain, infinite precision, as long as you spend a long enough time. That means that you can make the output frequency of a PLL exact. It is an exact relation with the input. So if I have, well, you can't make an infinitely precise clock, but you can make, I guess, I don't know about the rubidium crystals or the, well, you can buy temperature controlled oscillators that maybe have a few ppm change, but on a chip with components that vary all over the place, you can actually make extremely precise frequencies, extremely precise relationships between the output frequency and the input frequency, because you have infinite gain. And that's cool. Let's go into the blocks a bit. So we need an oscillator. The oscillator here can be an RC oscillator, it can be a ring oscillator, it can be a LC oscillator, so actually where the resonance is set by an L and a C. That's quite common in radios. It can be anything where you can control a pin coming in, which changes the frequency coming out. That's the basic principle. You have a control node. In this case, it's a very, very simple, stupid ring oscillator where we control the VDD of the ring oscillator, and that will obviously change the frequency of the ring oscillator. But one of the key parameters that you actually have to extract from simulation is what we call the KVCO, or the oscillator gain. Now that's defined as 2 pi with the delta frequency divided by the delta control voltage. In this case, we have voltage as a control input, but it could as well be also, maybe it's a digital controlled oscillator where the input value is the digital bit, and then it's the digital to frequency change. But the important part is how much does the frequency change as a function of the control voltage. Now, I'm going to show you the ring oscillator later, but for now, just have a mental image of a ring oscillator with the VDD of the inverters being controlled directly by this VDD ROSC. In that case, it shouldn't surprise you too much that when we simulate across corners and across temperature, this KVCO changes a lot. In the case here, I think the derivatives is about 1.6 for the typical corner, 1.6 gigahertz per volt or something. But the important part is your ring oscillator needs to have coverage of the frequency that you actually want out, in this case 512 megahertz. It needs to have that across all corners. And also, when you look at stability, you probably need to look at the KVCO, so the gradient of these lines in your PLL model, which you might write in Python, across corners to check that it's stable. But this is sort of, you make your oscillator, you check the KVCO, and you use that number in modeling of the PLL. I've put in the link to a PLL that is on my GitHub, and also includes the simulation, transient simulation of the ring oscillator to extract this picture and the KVCO. The second thing is the charge pump and phase detector. So we're comparing a divided down feedback clock here of 60 megahertz with a reference of 60 megahertz. And then there's a special block called the phase detector that compares those two and gives error signals, whether the two phases are aligned or not. I'll show you a little bit after, but here I would recommend that you sit down. It's not a complicated circuit, but that you actually draw yourself so you understand how it works. And then it basically tells the loop whether we should increase the frequency or decrease the frequency. So that's this up and down signals. So in the charge pump, we add some current, or we subtract some current or charge. The gain of the charge pump will be set by the current in the charge pump divided by 2 pi. So that's sort of the contribution that you get every period in terms of phase. For the loop filter, I'm sure there are many different ones. Here I've used the one from the book, which is actually I don't have the picture of it, we'll see it later. It's basically a resistor, capacitor, and a parallel capacitor, which gives you this loop transfer function. And here you can read the book and you can figure out what loop filter you want to use. Or if you're doing digital, maybe you have to read some papers. But the principle is we have our charge pump signal, which is now at 16 megahertz, pumping up and down, trying to control the frequency of the output. And we need to put in a low pass filter there. such that the average value of the charge pump actually just contributes to the change in frequency. In the PLL I've made, just to demonstrate the concept, I've also had to put it in a buffer because the loop filter voltage, that's quite high impedance. It's directly into the capacitor, and I don't want any current flowing into my VDD of the ring oscillator because that's actually pulling current because the inverters pull current. So in this case, I'll put in a buffer, unity gain buffer. For the divider, we'll have a look at the contents there, but that's simply a digital divider. Now, interesting question is, in Bluetooth, for example, we have to generate 2400 megahertz, but we also have to generate 2402 because that's the first advertiser channels. Actually, we don't use 2400, but we need to use 2402 and 2404. Now, if you want to divide 2400 and get a number that is 16, I think that is 150. But what is it for 2402? Well, it's definitely not an integer. It's a fractional number. So it turns out that it's also possible to make what's called fractional PLLs, and what you do then is that you have two dividers, where you sometimes divide by 150 and sometimes divide by 149, and you use a sigma delta, which makes sure that the average division ratio has quite low noise. So you actually use a sigma delta modulator in the divider here. For that, well, there are many books on PLLs, and there are many papers on PLLs, and you basically have to study those by hand. There is a really good book on PLLs by Besad Razavi. I don't have it here right now, but I'd recommend you have a look at that. Okay, so in the end, we can get a loop function, a loop transfer function. I've put in the model that I've used for the PLL, and then you can check the stability. I think if I've done it right, the stability here is 66 degrees, which is sort of okay-ish. Now, when I simulate the PLL, to me it doesn't look that pretty. There might be something going on here, but at least it settles, and it will settle here to exactly 512 megahertz. Now in about 8 microseconds. Takes a while to simulate though in ngSpice, so it's probably possible to improve this PLL quite a lot. The first thing I would start with would actually be the ring oscillator, which has probably too high kVCO. So let's look at the schematics. Unfortunately, I noticed when I power up Xschem, I can't really show the picture, so it has to be the PDF. Sorry about that, but anyway. Okay, so the ring oscillator, we have it's 9 stages. So we have the first stage is a NAND, and that is to make sure that the ring oscillator start up in a defined state. And then we have 8 more inverters. Those are connected in series, and they're powered from the VDD ROSC. Now, the VDD ROSC will drift up and down. It might be down to 1.1 volt, or it might be up to 1.6. Which means the output of the ring oscillator that goes into, let's see, here, the level shifter. Well, we need to level shift it. So we need to step it up to the VDD, which is 1.8 volts. And then it's just buffered. Now I've added, I probably just added a second inverter here to make sure the load on the level shifter is equal. The divider, that is based on purely digital. Let's see, CK, and then we need to find CK. Yep, so we have CK here, and the QN, so the, can we zoom in? Oh, sorry. Let me do like this, and zoom in a bit. So the QN of the flip-flop, that feeds back to the D, which means that the Q will toggle half as often as the CK. So this is, I think it's called a, is it called a ripple counter? I don't remember. But then you feed the D5 as the clock for the next stage, and then you can sort of divide by 2 each time. So this is a very simple way of generating divider. Be a bit careful with this one though, because it's easy to get hold time violations if you don't have the right flip-flops. Yeah, the current bias, that's just diode-connected NMOS with a power down transistor. And this is the op-amp that takes the loop filter voltage and then buffers it to drive the inverters. Here it's a simple LDO actually. So we have a differential pair with a current source and a first stage converting from differential to single-ended that is driving a PMOS, and that LDO is fed into a capacitor array, which is then likely our dominant pole. So here we have a dominant pole at the output, and that feeds the ring oscillator. Then we have the loop filter. So this is, here we have the charge bounce signal coming in, and you can see the second input here, the VLP-Z. That's just to set the initial voltage on the capacitor, the big capacitor. So here we have a small parallel capacitor with a, I guess this becomes a 0. So you have a resistor and a capacitor. For details on how to calculate these type of systems, I would recommend you actually read the book. It has good descriptions on how to, once you set up the system, how to do the equations and how to make steps to get the correct phase margin for your PLL. Charge pump. So here we get a signal in from the phase detector, whether we want to go up or down. So in this case, we have the VBN coming from the diode-connected transistor that feeds into 2 equal transistors. So the current coming out here will be 1 microamp. And then we mirror that current around with a PMOS mirror, and then have 2 switches, 1 PMOS, 1 NMOS. Which means that when we go up, then we connect the PMOS in, and we'll feed 1 microamp into the loop filter. When we go down, then it pulls out. And then we have the phase detector. So this is just a copy of the phase detector in the book. We have 2 flip-flops, and we have the CQRF coming in on the clock, and we have the CK feedback coming in. So every time one of them strikes, then we'll feed the value from the D's here to the Q. And then that's fed back through a NOR. So what I recommend you to do is sit down and then draw the state diagrams for this and figure out what happens when the CQRF strikes and what happens when the CK feedback strikes, and then work through it. It's best to see yourself. And to be honest, I've done it multiple times, but I keep forgetting it. But at some point you just go, well, this works. Fine. I should also mention these are what we call true single phase clock flip-flops. So they use dynamic logic. Yeah. That's just startup circuit. This is the level shifter. So if you've never seen a level shifter before, this is the concept. You have your input and your input inverted. That drives a PMOS latch, which shifts the signals up to the high voltage. Okay. So that, if you want to play around the PLL, if you want to clone it, if you want to make it better, which I'm sure you'll be able to, just change the ring, change the oscillator, then at least you have a starting point. You have something to play with. And I'm no PLL expert, but I know a few PLL experts, and PLL experts are very valuable. This is a complex block. It is really fun to do, and you can make a career out of PLLs. I wanted to touch on a couple of PLLs that you'll find in Journal of Solid State. So if you go into the Journal of Solid State, you will always find papers on PLLs. So PLL is also a type of block like an ADC that you can actually make for a specific purpose, as long as you know the reference and you know what the output frequency is going to be. But you will see that there are multiple different ways of doing PLLs. So in this case, we have what I just showed you with a simple divider, and then we have what we call an ADPLL, where we have a divider, and then we have a digital to time converter and a time to digital converter. So this is sort of a slightly different implementation of the phase detector. And then there's likely, well, it's actually a digital loop filter, and, well, something other fancy. I don't remember what the ASPLL stands for. But as you can see, the type of PLLs that are made, they can be quite complex. But the principle is the same. So in this case, we actually have a bulk acoustic wave oscillator that gives us the reference frequency that feeds into some sort of phase detector. It feeds into a charge pump, pumping up and down, and here you can actually see the current is also led to ground and VDD, because you sort of, I think they do that to, well, it's probably something with linearity and spurs, because when you turn the switch off or something, then I would assume that changes your current a bit. I'm not sure what they do here, but I'm pretty sure it's related to the charge that you feed in per clock into the loop filter. You want that to be the same and sort of independent of the switching pattern that has come before. Okay, then we have a loop filter, similar to what I showed you, but there is a second filter here, voltage filter. So the first thing here is sort of more current, generates a voltage, and then we have a low pass filter. And that feeds into a oscillator where we control the capacitance of some voltage dependent capacitors, varactors, variable capacitors. So in this case, most often you'll have your resonance tank, which is the combination of inductors and a set of fixed capacitors to get it roughly right. And then you have a tuning part where you finally adjust the frequency by very small adjustment to the capacitance. And here it's just using the fact that the voltage bias across a NMOS or a PMOS for that matter changes the capacitance. And then we have a huge buffer driving a 20 gigahertz output and blah blah blah. And here you can see the sort of the sigma delta feedback divider, where you have the fractional word that you want, and then there is sort of a sigma delta modulator fancy thing. This is first order. Okay, yeah. But you can actually generate frequencies that are not an integer relationship to your input frequency. PLLs have a couple of problems. One of them is what we actually want is a very clean clock. But we have a system with clocks inside it, 16 megahertz. We have maybe a fractional loop sigma delta that moves around, and those generate unwanted frequency components, which we call fractional, or we call spurs. Now, there's also a noise floor here, and the noise floor needs to be a certain level for different applications. For example, for radio, you need quite, well, relatively low noise. But for Bluetooth, for example, it's not that horrendous noise requirements. But for LTE, then it becomes more horrendous. So the type of PLL and how much current it's going to use is really dependent on what you're going to use it for. But these fractional spurs, that's something that comes with advanced topologies like sigma delta based ADC, sigma delta based fractional dividers, and it also comes with, well, it might be as simply as your MCU clock coupling to your inductors in your VCO. So inside the voltage control or the digitally controlled oscillators, if you have inductors in there, then it can pick up the magnetic field from anywhere else on the chip, and you can actually get spurs. Sorry. Which is why quite often when you make PLLs for radios, you probably need a few tape outs to get it right. you won't be able to simulate everything before you actually have something that can work in a high volume. It's hard, which means it's fun. The last one is just showing a different type of application. This is for FMCW radar, so radar where you might want to measure distance. But the reason I'm showing this is there are different ways of changing the frequency of the output, because if you were actually doing GFSK or Gaussian frequency shift keying, well, you have your reference frequency, 60 megahertz or 32 megahertz, and you have your output frequency. But what we actually want to do is change the output frequency as a function of a modulation. And in that case, you can either actually change the division ratio in sigma delta, or you can do what's called a 2-point modulation, where you feed in the modulation signal to the VCO and you feed it to the feedback divider, which means that the loop doesn't see the modulation signal. Fancy. Cool. And I guess the last one here is some other proposals that they had, which they thought were brilliant. You can find the, well, just Google the title of the papers and you'll find them. I might add them to the reference notes. Okay, thank you.